In this video, we're going to take a slightly different perspective as far as these Power and Taylor series are concerned. Here's our big question. So, given f of x that is, let's say, infinitely differentiable at x equals a, can f of x be expanded or represented as a Power slash Taylor series, right? So in other words, if I have a function and let's say, one of our elementary functions, can we now write that or expand that or represent that function as a Power Taylor series, right? And again, the reason why I keep using these two words is because Taylor, at the very least, gives us a formula for the coefficients, right? And if those coefficients can be used in our Power series form, the only other question, which we addressed in the previous video, was, okay, what is the interval of convergence of that series? And what is the radius of convergence? All right, so we're going to answer this using a couple specific functions that we're used to. So here's our function. Let's say we have the function 1 over 1 minus x. And here, and if you remember, this was the function that I showed with those animations, where we saw kind of a strange behavior with those Taylor polynomials. Well, let's see now if we can actually represent this as an infinite series, and then in the same breath talk about its interval of convergence, right? Now, let's say we want this to be at x equals 0. Again, just for convenience, we're going to take the center to be at 0, which makes this a Maclaurin series. If we come up with one, right, it will be the Maclaurin series. Okay, so let's take the Taylor approach, and we are going to try to find a formula for the nth derivative, right? So in fact, let me write down what our goal is. So our goal, so k goes from 0 to infinity, I would like to find a coefficient. Now, let me remind you of what the Taylor coefficients are. It's the kth derivative, and in this case, it will be evaluated at 0 over k factorial times x, and then I'll write this x minus 0 to the kth power, right? So the thing is, we need to come up with a formula for the kth or the nth derivative, like the general derivative of this function. So let's see if we can do that. So I am going to rewrite this as 1 minus x to the negative 1. And I'm gonna go ahead and start differentiating, right? But I'm not going to simplify too much, right? Because what we want to see is a pattern from which we can determine the kth or nth derivative, right? So let's look at what our first derivative looks like. Bring down the negative 1, keep the inner, subtract 1, and then we need to multiply by the derivative of the inner, which is negative 1. All right. So again, this is where I'm not going to simplify too much, because yeah, if we're doing this by hand, then yeah, we like to simplify this, right? But that's not what I'm going to do. And let's keep going. So let's look at the second derivative. Well, the negative 1 comes down. Now the negative 2 power comes down. And then keep the inner, subtract 1, and then bring down that negative 1, and then multiply again by a negative 1. Right? So this is the pattern that I'm going to write down a few more terms so that we can see it, and then we can identify what exactly is going on. right? So third derivative, I'll have bring down the -1, bring down the -2, bring down the -3, keep the inner, subtract 1, bring down that -1, bring down that -1, and multiply by, again, the derivative of the inner, which again is -1. So if you notice what is going on here, we have the same number of negative signs in front here as we do here. So essentially, all those negatives will go away, right? If you haven't seen it yet, let's write down what the fourth derivative would look like. -1 times -2 times -3 times -4. Then I'll have the quantity 1 minus x to the -5, and then I'll bring down all those -1s and then multiply by another -1. And again, all these -1s that I'm multiplying here after, that's due to the chain rule, right? So look at what's going on here. Again, I have the same number of negative signs in front as, I guess, at the back, right? So all the negatives will go away. Let's see if we can write down, but then look at what's left. I have 1 times 2 times 3 times 4 in front of the fourth derivative, but that sounds like a factorial. So it's almost like, let's see if we can write this down, this fourth one now, in a slightly different way. So I have 4 factorial here in front. And then I have the quantity 1 minus x. Now this exponent it's the negative of 1 more than the order of my derivative. So I can put a negative sign there, and then in parentheses put a 4 plus 1 there, and then that gives me the -5, right? And then, as I said, all these negative signs, they cancel out with these negative signs, so I don't even need to write the -1s anymore, right? So here is a not quite simplified version, but it's a good version of to see the fourth derivative, because then it gives us an idea of what the nth derivative is going to be. The nth derivative, you're going to have an n factorial in front. You're still going to have this 1 minus x, and then in the exponent, you'll have the negative of the quantity n plus 1, like that, right? And that's what we need to figure out what goes here, right? So I'm going to keep it on this side now. So here is our, what we would hope is our power series expansion of this, right? So we'll have k going from 0 to infinity. So what we have to do is take this nth or kth derivative and evaluate it at 0. So if I plug 0 in here, all I'll have is 1 to this particular power. So in fact, let me not simplify it right away. So I'm using this formula. I'm going to take, technically this should be k, because I'm looking at the kth derivative. So it's k factorial, then I'll have 1 minus 0 to the negative k plus 1 all over k factorial, and then I'll have x minus 0 to the k, right? Well, let's see what happens. We have, this is k equals 0 to infinity. The k factorials go away. They cancel out because the Taylor formula has a k factorial in the denominator. For this specific function, the kth derivative has a k factorial here. So these cancel out. Let's cross those out. And then I have 1 to a certain power. Well, that power is always going to be 1. So I have a 1 there. And then all I'm left with is x to the k. Well, that's pretty interesting, right? So again, based on Taylor's approach, we got this formula for the nth derivative. And notice that we can continue doing this forever, right? This function is differentiable for all value, well, I'm sorry, it has derivatives of all orders at x equals 0. But then let's write this out. Let's see what it looks like if we write it in the expanded form. This is when k is equal to 0, 1 plus, and then x to the first power plus x to the second power plus x to the third power plus dot dot dot. And what I have interestingly here is our wonderful geometric series. So this is geometric with first term 1 and common ratio x. So it seems like this function, this pretty simple function, 1 over 1 minus x, has this power series expansion. However, what do we know about the geometric series? It only converges when your common ratio is between plus or minus 1. So let's write this down, right? So f of x, which is equal to 1 over 1 minus x, can be represented by this power series, k equals 0, k going from 0 to infinity of x to the k, provided our x is between plus or minus 1. So provided we have this, right? And then this is the interval of, I'll just say, which is its interval of convergence. And what is pretty remarkable, this is kind of full circle, because if I think about our formula for the geometric series, remember the geometric series says if I want to write down the summation of this, it's a over 1 minus r. So I'll just put this as a note, that a over 1 minus r is equal to 1 over 1 minus x, which is exactly our original function, right? So this is interesting because it shows us for functions that we can differentiate infinitely many times, we can use our Taylor formula, but now in the context of a series. So it's not we can't call this a polynomial anymore because our expansion is not, it doesn't have finitely many terms. It has infinitely many terms. But that approach can now be used to expand or to represent some of our basic functions using power series, right? So that's really interesting. So now, I never thought you'd be able to do this, but what this implies is that our function 1 over 1 minus x is actually equal to this power series for, again, values of x between 1 and negative 1. So once we are outside of this interval of convergence, then this equation is no longer true, right? So again, it's kind of interesting to kind of look at both of these. If I look at this purely from a basic function standpoint, I would say that the domain of this function is all values of x not equal to 1. However, if I think of it now in terms of a geometric series, it's way more restricted in the domain. This part of it, right, is valid when our x is between negative 1 and 1, this interval of convergence, right? So it's like the interval of convergence is somehow a subset of the domain, right? So if I want to expand certain functions using a power series, I might have to give up a big chunk of the domain. But it's not all bad, right? As actually we'll see this in future videos. where there are things we can do to modify the interval, or if we need convergence on a different interval, then there are some things that we can do to this sort of basic result. And this is one of the standard results as far as going from a function to a power series. All right, let's take a look at one more example of this process. And we're only going to do one more, because in the next video, you're going to get some really good news, as far as this process is concerned, right? Going from a function to a power series. But let's take a look at what about our famous e to the x? Such an important function. Let's see if we can do the same thing for this one. All right. So e to the x. Well, the first derivative is e to the x. The second derivative is e to the x. Yeah, so, in a very basic way, the nth derivative has to be e to the x. And let's find the Maclaurin series expansion for this as well. So let's see when x is equal to 0. Let's see if we can expand this using a power series. So let's write down our formula again. K going from 0 but now to infinity for the full series. And it is the kth derivative evaluated at 0 divided by k factorial times x minus 0 to the kth power. But if all our derivatives are e to the x, then e to the x evaluated at 0 is just going to give us 1, right? So we'll have a 1 in that numerator. We'll have a k factorial there, and then this simplifies to x to the k. And there we go. So when you think about it, these are the coefficients now, right? And then of course our center is at 0. That's where we started. But the question is, for what values of x? In fact, let me rewrite it. So k going from 0 to infinity, you'll have x to the k over k factorial. So my question now is, for what values of x is this power series, right, a perfect representation of e to the x? In other words, I can replace the power series, or I can replace the function with the power series, knowing very well that they will give me the exact same result, right? So let's see if we can figure out the interval of convergence for this. Well, this is no longer geometric, right? Because you have a k in the exponent, but then you have this k factorial in the denominator. And with the k factorial, we like to use the ratio test. So let's look at the ratio test in terms of for the absolute values, right? So here is the series of absolute values. I'm going to write the series down and then apply the ratio test. So the series of absolute values, it's this one. You just put absolute values around everything. So x to the k over k factorial. And then we know we can write this as the absolute value of x to the k divided by the absolute value of k factorial. I don't know if x is positive or negative, so I can't simplify this any further. However, the denominator can be simplified quite a bit. Well, it's simplified in the sense that k factorial is always going to be positive, right? As k goes from 0 to infinity, k factorial is always positive. So that denominator is always positive, so it looks like this. All right, and now let's use our ratio test, because we know the ratio test is very, very helpful with our factorial. So using the ratio test, Let's set up our a sub k divided by, a sub k plus 1 divided by a sub k. So take this expression, replace all the k's with k's plus 1. So x to the k plus 1, that is an absolute value, divided by k plus 1 factorial, and then multiply by its reciprocal. Since we're dividing by a sub k, we have k factorial over the absolute value of x to the k. And then let's go ahead and use some properties of the factorial and exponents and absolute value all together in one big swoop. So this numerator here can be factored as x to the k in absolute value times the absolute value of x. This denominator here, using the recursive property of the factorial function, this is k plus 1 times k factorial. This numerator is going to be left the same, because you can see why, stuff's going to cancel out. And then at the bottom here, this one will be left the same. So what cancels out, right? The absolute value of x to the k, absolute value of x to the k. K factorial here, k factorial there. So the ratio in its most simplified form can be reduced to the absolute value of x over k plus 1. And that's it. So now the ratio test says take the limit as k goes to infinity of this, and that's our r. So it's the limit as k goes to infinity of the absolute value of x over k plus 1. But since the absolute value of x does not involve k, I can factor that out and put it as x times the limit as k goes to infinity of 1 over k plus 1, right? And as k goes to infinity, 1 over k plus 1 approaches 0. So I have the absolute value of x, whatever that number happens to be, and then times 0. But that product is going to be 0, which means my r, no matter what my x is always going to be less than 1. So what the ratio test is showing us is that no matter what value of x I have here, this r is always going to be less than 1. So therefore, this power series converges absolutely for all values of x. Wow, that is remarkable. And that's this, remember, that was the second possibility in our theorem. It says that there are some power series out there that will converge absolutely for all values of x. Well, what in the world does this mean? It means that my function e to the x can now be written as this power series, k going from 0 to infinity, of x to the k over k factorial. And let me write out a few terms here. So when k is equal to 0, you'll have 1. When k is equal to 1, you'll have x. When k is equal to 2, you'll have x squared over 2 factorial. When k is equal to 3, you'll have x cubed over 3 factorial. And if I continue that expansion indefinitely without end, then the ratio test just proved, or we just used the ratio test to prove, that our e to the x function can be written in this power series form, and this is for all values of x between negative and positive infinity. So the interval of convergence for this power series is infinite. That is pretty mind-blowing, that our simple little function, e to the x, now has a form that can be represented, a power series form that represents the e to the x for all values of x. And so this process that we did it for the geometric series, and I always like to do the geometric series first because it's simpler and it's a result that we've used several times over, and then it can be then applied to other functions. So like e to the x, and it turns out this can be done for the sine of x, the cosine of x, the ln of x, and so forth. So all of these functions that you've studied previously, starting, maybe pre-calculus or college algebra, you're now seeing that they all have a certain way of being represented or written as power series. Now, some might not work for all values of x, like we saw with the geometric, but many of you'd say the most important ones, like e to the x, is pretty up there in terms of importance, can be represented in power series form for all values of x. So in the next video, instead of deriving a lot of these, I'm going to kind of give you a short list of all the important ones in a nice little table, and then we're going to see how we can use that table to our advantage and find other power series representations for functions. Not necessarily the really simple ones like e to the x, but what if you had like a e to the x squared or e to the negative x squared, something like that? Can that be represented as a power series? So we're going to continue looking at this, but then we're going to make use of basically a set of templates that, like I said, will make you a lot happier not having to derive everything from scratch. And I'll see you soon.